Good morning, students. Today we will discuss the existence of continuous extension of a function from a Tikhonov space into compact T2 space. And for this, there are two lemmas. One of the lemmas we discussed yesterday, and now the second lemma is to prove that the mapping E from the topological space X into beta X, that is a homeomorphism if and only if the topological space X star is compact. So first of all, let us suppose the mapping E from X into beta X is a homeomorphism, and we claim that this topological space X star that is compact. Now, by definition of beta X is compactification of the topological space X star. So that is compact, and X is homeomorphic to beta X. So we can say that X will also be compact. Now, in the converse part, we are given that the topological space X star is compact, and we are to prove that the mapping E from X into beta X is homeomorphism. Now the mapping E from X into beta X, that is evaluation map. It means it is 1-1, continuous and open. To prove it is homeomorphism, it remains to prove that this mapping is onto. It means we are to prove that E of X is equal to beta X. Now, by definition of compactification, the closure of E of X, that is beta X. Now X is compact, E is continuous map. Therefore, E of X, that is a compact subset of beta X. Now beta X is T2 and compact subset of T2 is closed. Therefore, E of X, that is a closed set, and therefore its closure will be identical to itself. So we can say that beta X is equal to EX from here, and this proves that the mapping E is onto map. So this proves that the mapping E is homeomorphism. So this completes the proof of second lemma. Now we will do the proof of main theorem, in which we show the existence of continuous extension of the function f. Here f is a function from x into y, and this is continuous function. Let us define two families of the functions. First family we have denoted by bx. This is a collection of all those functions k which are defined from x into the unit interval. This is a collection of all such continuous functions defined from x into unit interval I. Next we define the family by. This is the family of all the continuous functions from y into the unit interval I. Now let us define a mapping f star from the family by into the family bx. To define this mapping, let us take an element h belonging to the family by. By definition of this family consists of the functions defined on the set y into the unit interval I, and these functions are continuous functions. So h belonging to this family means h is a continuous function defined from y into the unit interval I. Now f is a function from x into y, h is a function from y into y. So the composition of H with F, that is a mapping from X into I, and that will also be continuous function. It means HOF is a function from X into I which is continuous. So by definition, this function belongs to the family Bx. So we can define the function f star by f star of H is equal to composition of H with F. Now, next we define the mapping f double star from IBX into the set IBY by taking an element y from here. F double star of y is equal to y of f star. Now, by the first lemma, this function is continuous function. Next we define evaluation maps on the set X and the set Y. So first we define evaluation map E from the set X into beta X. This is evaluation map on the set X. Next we define G, an evaluation map on the set Y into beta Y. This is evaluation map on Y. Thus we have the following diagram. Evaluation map E, that is a mapping from X into beta X. F is a mapping from X into Y. G is a mapping from Y into beta Y. F double star, that is a mapping from cube IBX into the cube IBY. So we have this diagram. Now, next we claim that the composition of the mapping F double star with E is same as the composition of mapping G with F. In order to prove this, we will have to prove that the image of every element of X under these two mappings that is same. And in order to prove this, we will have to further prove that F double star of E of X of H is equal to GOF of X of H for every H belonging to the family BY. Now, firstly let us find this part, image of X under the mapping F double star of E. By definition of composition of two mappings, this can be written as F double star of E of X. Now this is further EX of F star. Therefore, the image of H under this mapping, that is equal to EX of F star of H. Now this can further be written as EX of F star of H. F star of H, that is HOF. And this is further is equal to H of F of X. And this is further is equal to G of F of X of H. So we can say that the mapping F double star of E is same as the mapping GOF. Now, next we claim that image of beta X under the mapping F double star, that is contained in beta Y. So let us consider F double star of beta X. Now by definition, beta X is the closure of E of X. Now we know that if a function is continuous, then image of closure is contained in the closure of image. So F double star of closure of E of X, that will be contained in the closure of image of E of X under the mapping F double star. Now F double star of E of X, that is G of F of X. F of X, that is Y. So this will become closure of G of Y. Closure of G of Y, that is beta Y. So we have proved that F double star of beta X is contained in beta Y. Now the mapping G, that is evaluation map on Y, and this Y, that is a compact topological space. Therefore, by second lemma, the mapping G is homeomorphism. So that will be 1, 1 on 2. So inverse of this mapping will exist. G is a mapping from Y into beta Y. So G inverse will be a mapping from beta Y into Y. Now F double star, that is a mapping from beta X into beta Y. So we have the following diagram. E is a mapping from X into beta X. F is a mapping from X into Y. G inverse is a mapping from beta Y into Y. And F double star is a mapping from beta X into beta Y. Now we are to take a mapping which is continuous extension of function f. That mapping we can take a mapping from the set beta x into y. That will be the composition of these two mappings. So we can have the mapping f bar from beta x into y. That is a mapping. And this mapping can be taken as G inverse of F double star. This is composition of two continuous mappings. So that will be continuous. Now, in the last step, we are to prove that composition of F bar with the mapping E, that is F. So let us take X belonging to the set X and let us find the image of X under this mapping. Now F bar, that is G inverse of F double star. So this will become G inverse of F double star of E of X. Now this can further be written as G inverse of F double star of E of X. F double star of E of X, that is G of F of X. G inverse G, that will become identity. So that will become identity of F of X. So that will be F of X. So we have proved that for every X belonging to X, F bar of E, that is F bar of E of X, is equal to F of X. It means the mapping F bar of E is same as the mapping F. So this completes the proof of this theorem.